This figure shows the blackbody spectrum with intensity plotted versus wavelength at 4 different temperatures: 2000, 3000, 4000, and 5000 Kelvin. The colors in the background correspond to the colors associated with the wavelengths shown on the x-axis. We can see that at 2000 Kelvin, the peak in the spectrum occurs in the infrared, whereas at 5000 Kelvin, the peak occurs in the visible region. In other words, at 5000 Kelvin, the color of the most intense radiation from a black body is yellow. This observed shift in the peak to shorter wavelength as temperature increases is known as Wien's displacement law. Mathematically, it's typically written as lambda max equals B over T, where lambda max is the wavelength where the strongest emission is observed, T is the absolute temperature in Kelvin, and B is a constant equal to 2.898 times 10 to the negative 3 meters times Kelvin. This equation essentially says that lambda max is inversely proportional to the temperature. Lambda max is equal to a constant, B, times the inverse of T. Estimate the peak wavelength of radiation coming out of a person's ear. Using Wien's displacement law, lambda max is equal to B over T, where B is 2.898 times 10 to the negative 3 meters times Kelvin. If we assume the person has no fever with a normal temperature of 98.6 degrees Fahrenheit or 310 Kelvin, we find that lambda max is equal to 9,350 nanometers. The reciprocal of lambda max is 1,070 reciprocal centimeters. This is in the mid-infrared region. We can see that to be able to detect emissions from objects near room temperature, we would need a detector that is sensitive to infrared radiation. Ear thermometers and night vision goggles use infrared detectors.